Concrete is by far the most widely used construction material in modern infrastructure and buildings. However, due to its brittleness, concrete is susceptible to problems under dynamic loading. The low impact resistance of reinforced concrete structures often leads to dramatic consequences in cases of traffic accidents, earthquakes, rock slides, or terrorist attacks. Considering the high social, economic, and ecological risks involved, concepts need to be developed to increase the impact safety of critical infrastructure.
In view of the high relevance and urgency of the problem, as well as the wide range of engineering and the social aspects to be taken into account, TU Dresden has formed a multidisciplinary research training group on impact resistance. The goal of this project, sponsored by the German Research Foundation, is to develop new materials and design approaches for the strengthening of existing jeopardized concrete structures.
The strengthening materials presently under consideration are mineral-based, fiber-reinforced composites of very pronounced tensile ductility and high durability. Every constitutive phase can be tailored with respect to its function and interaction within the composite.
The cementitious matrix assumes the role of a solid shell with a high physical and mechanical compatibility with a concrete substrate. We reinforce the matrix with short polymeric microfibers to give it high inelastic deformability through the controlled formation of multiple fine cracks. This ensures high energy dissipation and damage tolerance in the strengthening layer.
2- or 3-dimensional textiles are other novel types of reinforcement. Metal wires or multi-filament yarns made of high-performance carbon or polymer fibers are weaved into continuous structures with the required geometric and mechanical properties. The role of such textiles is to ensure favorable stress distribution in the strengthening layer and a strong envelope for the element to be strengthened.
The combination of short fibers and textile reinforcement can provide for a highly advantageous synergetic strengthening action. The development of new high-performance materials and adequate application technologies are, however, only the first step. To achieve our goals, fundamental multi-scale, experimental and analytical research is needed.
The complex micro and mesostructure of the composites developed and the resulting complex mechanical behavior at high loading rates make it necessary to design and build specific testing facilities which enable accurate and consistent material characterization. This is done by decomposing the structural impact actions into their primary loading modes, such as tension, compression, and shear, and applying them at the level of the composites and of their constituents. In the next step, an advanced testing machine is used to reproduce severe impact scenarios on large structural elements under controlled laboratory conditions. Heavy projectiles are accelerated to speeds of up to 150 meters per second to achieve partial or complete structural failure under hard impact. Such experiments enable a quantitative assessment of the impact performance of structural elements, both with and without strengthening layers. Considering the novelty of the materials developed and the large span of the scales of interest, adequate numerical methods are needed for a better understanding of the experimental findings and, eventually, for predicting structural behavior under various loading conditions. In close collaboration with their colleagues who are carrying out the experimentation, 4 young researchers are working on a system for advanced numerical analysis at the micro scale, the scale of the composite materials, and the structural scale. The fiber-reinforced composites are modeled individually by taking into account their discrete microstructure and microscale inertia. The resulting simulations, with a discrete representation of micro and continuous reinforcements, are considered to be virtual experiments with a well-developed capacity to separate intrinsic material behavior from phenomena induced by boundary conditions in the real experiments.
Aside from the engineering factors, the sustainability and resilience of the developed strengthening solutions are assessed already during the development stage. We believe that it is crucial to demand a certain awareness among engineering colleagues in respect of the economic, ecological and social impacts of their work.